Okay. Now we are good. All right.
Rohan,
Yeah.
you troll, turn on attendee stream sharing,
Oh, yeah, my bad.
or make me co-host or something.
Security. Share screen. Okay, you should be good.
Okay. Alright, nice.
Okay. So, today we are talking about dynamic programming. That took a while, but we are finally here. Okay, so, first off, what is dynamic programming? So, essentially, it is similar to recursion, but basically what we're going to do is we're going to store what we already found. So, it basically trades memory for runtime, and I think the best way to understand dynamic programming is just by going through a couple examples, okay? So, let's just first explain the basics. So memoization, right? You go top down and you break it into smaller instances of the same problem and you store those smaller instances. So in a typical Fibonacci thing, right, you're basically doing this tree, right? You do f6 is equal to f4 plus f5, which is equal to f2 plus f3, and so on and so forth. But what is the problem here? Anybody? What is the
Like you have a lot of repeated terms.
Yes, exactly. So we have a ton of repeated terms. So basically, the way that dynamic programming solves this, you basically store everything as soon as you find it, right? So we go to f6, we go to f4, then we say, oh, f4 is f2 plus f3, so we try to find what f2 is. We go f0 and f1. Okay, what are f0 and f1 called? Like in recursion, what are they called when we know what they are?
Wait, real quick, Rohan.
Yeah.
I still cannot screen share in the breakout room. Maybe try like, uh, making me co-host or something.
Yeah, yeah, that's probably the best idea. More. Okay, you're co-host now, so you should be good.
Alright, I will try now.
Okay, so basically, what are f0 and f1 called? Because we know what their value is. It's like what the recursion is based on. And anyone know what it's called?
The base cases?
Yes. So we basically have our base cases, right? So we know what f0 and f1 are. So now we can know what f2 is, which is 0 plus 1, which is 1. So then we store what f2 is, and now we know that f2 is 1, and we never have to calculate f2 again. So then we go back to f3, we find that, oh, we already know what f1 is, okay? We go to f2, we already know what f2 is, so we don't have to re-look up f0 and f1, so we get f3 is equal to 1 plus 1 is 2. And basically, you keep repeating this process based on the stuff you've already stored. Did someone just join? Chat. Okay, we're good. Okay, so essentially tabulation is just the opposite. Instead of going top down and storing what you find, you basically build it from the bottom up, right? So in this case, instead of just like starting from the top and then going down, we just start with f0 and f1. We find what f2 is, then we find what f3 is, and then so on and so forth up till f6, which seems a bit more, which seems a little bit more efficient, but it's basically the same thing. Okay, so now to solve DP problems, the two things you gotta determine are the state and the transition, right? So could anyone tell me what the state for Fibonacci is? That's basically like what you want to solve for. So what would the state be for Fibonacci? What are you trying to solve for? Anybody?
The nth term of the sequence?
Yep, you're solving for the nth Fibonacci number. Then your transition is, I mean, it's kind of on the slide, but yeah, what are the transition? Transition is basically how you determine one thing from previous things. So what would it be for Fibonacci numbers?
F of n equals f of n minus 1 plus f of n minus 2.
Yep, and whoops, I went too far. And then, of course, your base case is 0 and 1. Okay, so this is the naive approach. It's really bad because you had to redo all the heckin' work, so that's bad. But if we do top down, you basically have a lookup table, or lookup array, which stores your Fibonacci. Honestly, this is Java, which is why it's kind of nasty, but if you do it in Python or C, it's like way cleaner. But basically, you get the idea, right? Like, if it's not there in your lookup table, then you have to recompute it. But if it is already there, or if it's already there, then if it's already there, then you could just, like, use it, right? You just return lookup n if it's already there. Okay, and then the other option is you just start from the bottom, you set your base cases, and then you just build it up from there. Okay, so now let's think of a little bit more, like, less typical problem. So could anyone give me, okay, so first off, our goal is to tile this board with these tiles, right? So could anyone tell me like how many ways there are? Okay, so basically this is a 2 by n board, right? So let's say we just had a 2 by 1 board. How many ways are there to tile it? So just tile this one place.
1,
Yep, if we have these two. What about if we have 2 by 2?
2,
2, yes, 2, right? Because we could have vertical or we could have horizontal. Then what about 3? Now 3 makes it a little bit more complicated.
I think 5.
Right, you could have, so okay, so basically let's try to break this problem down, right? So how like we know that this block right here has to be covered somehow, right? So what are the 2 ways in which we could cover this block?
Vertically or horizontally?
Yeah, so we could either put one thing down or we could put one thing to the right. So now like for this one, what is the only option for covering this block?
Horizontal.
Yeah, you have to put another block right here. But now you can see that we have another 2 by n rectangle. So could anybody like see what the recursion might be? Like, so now we want to solve for 2 by n, so our state is obviously 2 by like n blocks, right? Then like what are their transition? Like how can we find the bigger problem, which is our 2 by 4 block, in terms of 2 by 3 and 2 by 2? Because we know, like, there's 2 cases, right? Either we put a vertical block and we're down to 2 by 3, or we put 2 horizontal blocks and we're down to 2 by 2. So what is 2 by 4 in terms of 2 by 1 and 2 by 3? I mean 2 by 2 and 2 by 3. How does case work, guys?
The number of ways to do the 2 by 2 plus the number of ways to do the 2 by 3.
Yeah, exactly, right? So you could fill up this 2 by 2 however the heck you want. And then to get it to 2 by 4, you just add 2 horizontal blocks. And then same thing for 2 by 3. For any 2 by 3 you do, all you gotta do, add a vertical block, and you are to 2 by 4. So essentially, we have found a state and a transition. What is our base case? And then we are basically done with the problem. What is our base case? Well, okay, well, how many ways are there to tile a 2 by 0?
0.
It's a trick question. Anybody have a better guess? How many ways are there to tile a 2 by 0 block? Come on, people. If it's not 0, what has it got to be?
1.
Yeah, exactly, right? Like, the reason it's 1 is because the definition of tiling something means that all the squares are covered, right? So if you have a 2 by 0 block, there's no squares to cover, so it's already all fully covered. So essentially, there's one way to do that. Then there's one way to cover a 2 by 1 block, right? Because you literally just the same as the tile. And then if we look at 2 by 2, it makes sense, right? You basically do 1 plus 1, and there's 2 ways to do a 2 by 2 block, right? You can either do vertically or you can do horizontal. Makes sense. So we basically solved this problem. It's very cool stuff. Okay. Now this is another typical problem. It's basically, let's say you start at the bottom left, right? And you want to get to the top right using only up and right movements. So what is this called in math? Does anybody know what this type of problem is called? If you guys do competition math. Come on, the common combinatorics problem. Anybody? What's it called? Starts with a B. Starts with a block. Come on. Nobody knows what it's called in math? Bro, aren't you guys, most of you guys are in math club? Come on. Okay, well, the answer is block walking, right? Like, this is basically a block walking problem. But obviously, block walking is easy, right? Like, okay, pretend these obstacles weren't there. How many ways are there to get from here to here using your math skills? Come on, people. Okay, Aiden, I know you. Okay, yes, Lisa, go.
10 choose 4. In this
Exactly,
case.
right? Yeah, basically, you can literally just do one expression in math and hooray, you already solved it. But if you add obstacles, it's not that straightforward, right? In normal math, you literally have to do casework, and like, casework is completely nasty. If you add more than one obstacle, it becomes like basically impossible, right? So a computer, though, could do this a lot more efficiently. So let us try to figure this out. So how many, okay, so let us start by, hold up. So let's just start from the left, right? We know there's one way to get to the starting point, right? Now let's try to find like how many ways there are to get to each point like on the grid. So could anybody tell me how many ways there are to get to this point?
1.
Yep. And because it's symmetric, there's also 1, right? Then what about this one?
Also 1.
Yeah, because the only way to do it is just by going straight up, right? You can't like go right and then like left because we're not allowed to go left. We can only go up and right. So the only way to do it is just go straight up. Okay. Then so we know that like for all of these it's just 1. Then how many ways are there to get to this one?
2.
Yeah, 2, right? But okay, so it's 2. But you gotta notice a pattern here. Like 2 is a sum of what?
1 and 1.
Yeah. So could anybody tell me why? Like why that makes sense? Why is this guy right here the sum of some ones? Like how? Where could we find a relationship? Where's the recurrence relation?
You can only get to that point from the point on the left and the point below it. So
Yeah,
you just add
exactly.
it together.
Yeah, exactly. Like the only way to get to this point is by making a right move from here, right? You could start here and then move right, or the only other option is you come upwards from here. So essentially, we could take whatever hacking path we want to get to this point, but the only way to get to this point is by taking a right from here. Or the same idea, we could take any path we want to get to here, but the only way to get to this point is by taking an up as your last option, right? So essentially, every point, so this is 2, right? It's a sum of 1 plus 1. That's how we got 2. So then if we do the same option, like same concept, we get that this is 3. And now we can just fill out our whole array, right? And what do we do when we get to an obstacle? How many ways are there to get to, like, what's our number going to be for the obstacles?
0.
Yeah, exactly. You got to make it 0, right? Because there's no way to get to an obstacle, right? An obstacle is unpassable terrain. There's no way to get onto it, right? So essentially, we just set these to 0 and then just do the same recurrence, right? How many ways are there to get to this guy?
1.
Yep, because of 1 plus 0, 1, then you get the idea, there's 0, so on and so forth. And hooray, we got our thing. What is our answer then? How many ways are there to get to here? Just read it.
56.
Yep, we literally have our answer just by using this one recurrence relation, okay? So essentially we get our answer. Our state was the number of ways to get to each point. The transition was you add the left and the bottom point, and then your base case is basically there's one way to get to anything on the bottom line, and there's one way to get to anything on the left-hand line. So how much time do we have? I want to code this one up because the examples we're going to talk about later are kind of complicated, so let us code it up. Okay, hold up. Log in. Okay, what language are you using? Any suggestions? I'm fine with anything. No suggestion? Okay, we'll use Python then. Alright. So let me just copy and paste my other file input output so we don't have to redo that from scratch. Give me a second. What are we doing? Obstacle chess. Okay. Okay. So this right here is my reading it in, right? So essentially now we basically have to. So basically what I did is I set all of our DP array to 1, right? Except for the obstacles which we set to 0. Now, could you guys tell me what we had to do now, right? Like we have everything on the bottom is 1, everything on the left is 1, and we have all the obstacles are 0. Now, what do we have to do in order to solve the problem? Okay, so let's look at our diagram again, right? We have all our 1s and we have our 0s. What should we solve first? Like which square do we which point do we have to solve first?
I guess we should identify the obstacles.
Well, yeah, I already did that, right? Like I set those to 0, so we know whenever it's a 0, it's going to be an obstacle, right? So but now that we have everything set up, now what do we have to do? Which one are we going to calculate of all these points that are free? What should we calculate? Which point? Which point is the only one we could calculate right now? Come on, there's. What order did we do it in?
1, 1.
Yeah, the only one we could do it here is 1, 1. Then where should we go from there? We could do this one, right? Because we have these two now, so we could do this one. Then we have these two, so we could do this one. And we'll just go to the right, and then we could do these, and then we could do these, and we could do these. So that's essentially the order we're gonna go in. So basically, we are going to do it for I in range, or for I in range M, which is the number of rows, and then for J in range N, we are going to go through it. So first we had to check we're not on an obstacle, right? So we're first gonna set dp, if dpij is an obstacle, which means it's 0, then we're going to continue, right? We don't wanna like recalculate it. It has to stay at 0 if it's already an obstacle. But if it's not an obstacle, then we have to do the sum of the other two, sum of the left and the bottom points, right? So essentially, let's set our current thing to 0, and then we'll add in the different things. So first off, we had to check, or actually we don't have to do this. We could just say dpij is equal to dpi minus 1, and we should probably do from 1, 1, because we have to start at 1, 1. Okay. I minus 1 j plus, what's the other one?
Ij minus 1.
Yep, ij minus 1. Okay, and then we basically are done, right? So essentially what we're going to do is we are just going to, what do we print out at the very end? What's our answer?
M, N.
Well, yeah, well, what's the index of that in our array? Or actually, yeah, you're right, yeah, right. Okay, hold on. So print dp m, n. Okay. So then I should probably make this n plus 1, okay, and n plus 1. So now now we just gotta put in our input. So what we're gonna do, hold up, okay, let's put our input in. So we're gonna call this obstacle chest.in. Okay. So essentially we have 4. Yeah, so we have 4 by 5, how many? 4 by 6, okay. 4 by 6. So essentially we have a bunch of free spots, 6 free spots, right? And then we have 2 obstacles, then a bunch of free spots. Then we have ... 2 obstacles, then a bunch of free spots, and then we have more free spots. Is this right? Looks right. Okay. Oh, whoops, I had to flip it, god dang it, because I did it the other way. Okay, hold up. Hold up. Okay, so essentially I coded it so it goes from here to here. So how do we flip this so that it's the same? Oh, we literally just, okay. Okay, there we go. Alright, so that should be the same. Let's try running it. Is that the same? Yeah, it should be the same. Nope. Okay, hold up. Oh, we had to go m plus 1. Wait, are you trolling? Oh, what? Oh, I got this one. Is it 6 or 5? Hey, you guys gotta debug with me. Let's do it. Anybody see the problem? I do not see the problem. Hold up. Okay, why don't we just print dp? Hold up. Print dp. 4 row in dp. Okay, let's try that. Alright, this seems about right. Right? Oh, okay, I see. Huh. Whoops, I gotta have this many. Okay. ... Okay. Hey, okay, there we go. So essentially you guys get the idea, right? Like basically we have to do a recursion in order to solve the problem. That's how I do it. Okay. Was that tabulation or memoization? Does anybody know which one it was? Memoization is top down. Tabulation is bottom up. So did I do bottom up or top down?
Tabulation.
Yeah, I did it bottom up, right? Because I basically set the base case and then did the immediate thing above it until I got to my thing. Top down, you start at your thing and then go backwards. Okay. Now, a harder DP problem, I'm just going to go through it really quickly, but essentially the idea is you want to find the biggest, longest common substring of two strings, right? So essentially, in this case, it is ABD, right? It has length 3. So the way we do this is, like, we can split it into smaller subproblems, right? Let's say we know that, so between ABCD and ACBA, what is the longest common substring?
AB.
Yeah, right, like, it's either AB, AC, whatever it is, the longest substring is 2, right? So now we want to find the longest substring of ABCD and ACBAD, right? So essentially that idea is we know we could take like AC, right? And AC, and if we add a D at the end, we know that this D could correspond to this D over here, right? So essentially, if we know the LCS of a smaller thing, we could find the LCS of a bigger thing. Basically, that's the idea. So essentially, if we do our state as this, then we could find the transition in terms of the previous strings. Okay, so let's think exactly how we could do this. So basically, the idea is, well, okay, so the basic idea is like if we have the longest common substring of like, okay, so basically the idea is we take out one of the letters, right? So we do ACBA and ABCD, and we find that the longest substring is AC, right? Then we could add in the D, and now our longest substring is C. And then we could do it for the other three cases, and then just take the max of them all. So that's the basic idea. It's a little bit of a complicated problem, but that's the basic idea. So I'm not going to go too in depth for it, but you could look over the presentation in your free time. This is a lot more complicated than the other algorithms. Okay. Okay, well, this is a little bit less complex one. So this is a common one in Yusuko Gold, but honestly, you guys are probably not into that much Yusuko Gold. But basically, the idea is you have a bag that can carry up to C weight, right? And there are n objects indexed 0 to n minus 1 with values vi and weight wi, right? And you want to find the most value you could take, right? So what's the problem with just taking the biggest value one? Anybody? What's the problem with just taking the biggest value? Any ideas? Well, basically the problem is like if you take the biggest value, then you might fill up your entire bag, which might be bad, right? Because you might as well take something that has a lot of value but also doesn't take up that much space. So the idea is you can't just directly do it using greedy algorithms, just take the best one, because then it might like not work out. So now the idea is you want to keep track of the best way to do a certain bag with the first like k objects and like taking up some amount of capacity, right? And you could choose whether or not you take any certain item. So essentially, if you take one of the items, you can't take, like your capacity jumps to a certain point. But if you don't take a certain item, then your capacity doesn't change. So essentially that's the idea here, you just take the best one of those options. And then here are a bunch of other things that you could do using DP, but I think the example that we went through are the more common ones. So because you guys are like not, like this is more of a Yusuko Gold problem, so I don't think you guys need to do it. So I'm just going to give you guys a flag, but do you guys have any questions about DP? Like, did you guys understand the first two examples? Because those are the more interesting ones. Any questions? Okay. Well, let me send the flag. Okay, did you guys all get it? You guys good? Okay, well, we are done for today, so feel free to drop out if you guys are done, but make sure to get the flag and submit it for points.
Thank you.
Yeah. Alright, see you guys. Hello. Are you here to ask a question, or you just haven't left yet?